Okay, let's jump right into this explainer. Today, we're talking about the absolute invisible guardians of our modern world. I mean, whenever you flip a light switch, charge up your phone, or just look at a city's skyline lit up at night, you're relying on a shockingly complex electrical power grid. But think about it. What actually happens when lightning strikes a massive transmission tower, or a huge tree crashes onto a high-voltage line? Without instant, super precise intervention, all that raw energy would trigger catastrophic, cascading failures. So today, we're unpacking the invisible math, the high-speed logic, and the frankly brilliant engineering that literally keeps our grid from destroying itself. We've got a really exciting lineup today. First, we'll look at how distance relays work, then we'll map impedance on an RX diagram. After that, we dive into the 3 zones of protection, followed by speeding up the defense, and finally, backups and breaker failures. Let's get to it. Section 1, How Distance Relays Work.
So, meet our main protagonist. In the power industry, folks usually just call this the 21 relay. Think of the distance relay like a highly trained bouncer at the door of a super exclusive club, constantly checking the ID of the electricity flowing through the line. And how does it do that? Well, it relies on an incredibly simple mathematical principle. It just divides voltage by current to find the impedance. Because the impedance of a transmission line is inherently proportional to its actual physical length, this clever little device can literally measure the electrical distance to a problem.
Now, to actually see this electrical world, our bouncer needs a bit of help. I mean, the relay can't directly handle the hundreds of thousands of volts coursing through the main line. It would fry. Instead, it uses a VT, or a voltage transformer, and a CT, a current transformer. These step those massive, lethal numbers down into a safe, manageable scale. By constantly comparing the voltage against the current, essentially checking the restraining coil against the operating coil, it can monitor the real-time operating conditions without blowing up.
And this brings us right to the central conflict of the whole system. Under normal, everyday conditions, your voltage is high and your current is steady. That combination creates a high impedance. This is our VIP guest, right? The normal load. But when a short circuit or a fault occurs, the voltage absolutely plummets and the current skyrockets. Suddenly, the math flips. The impedance drops massively. To the relay, this sudden, drastic drop is a giant flashing red light, signaling that a dangerous intruder is on the line.
Section 2. Mapping impedance on RX.
Okay, so we have the raw algebra of voltage divided by current, but just staring at an endless stream of numbers really isn't the best way to catch an intruder. Engineers needed to translate that dense algebra into visual geometry. And that gives us the RX diagram. It's honestly a masterpiece of electrical engineering. We plot the line impedance, which is represented as Z equals R plus JX, right on a graph. Your horizontal axis is resistance, or R, and the vertical axis is reactance, or X. Mapping it out like this creates a beautifully clear, defined visual boundary. You can physically see the safe load area versus the dangerous fault zones. If the relay's real-time calculation drops into a specific geometric shape on this graph, boom, it trips the breaker.
Back in the early days of power protection, engineers used literally the simplest shape possible, a plain circle centered right on the origin of the graph. If the impedance dropped anywhere inside this circle, the relay tripped. Simple, right? It was a really great start, and it provided a solid zone of protection. But if you look closely, there's a major geometrical flaw with this design. Wait a second. This plain circle has no direction, so how does it actually know which way the fault is? Think about this. If the relay is sitting at a substation, a fault could happen on the line directly in front of it or on a completely different line right behind it. Because the circle expands equally in all directions around the origin, this plain impedance relay is completely blind to direction. It might accidentally trip your power line for a problem happening miles away in the exact opposite direction. Not great.
But watch how the solution evolved. First, engineers tried a bit of a patch job. They added a straight directional line to physically block out the bottom half of the circle. It worked, sure, but it was pretty clunky. Then they evolved the design into something incredibly elegant. By shifting the entire circle up so its bottom edge sits right on the origin, they created what's known as the Mo shape. This shape inherently only looks forward down the line. It is just a beautifully elegant mathematical fix.
And the evolution absolutely didn't stop there. Today, we use the quadrilateral characteristic. Because modern digital relays aren't limited by old-school physical spinning disks, they can easily calculate straight lines and perfectly sharp corners. This gives grid operators the superpower to customize incredibly tight, precise borders to perfectly defend their specific transmission lines, completely avoiding false trips from heavy everyday loads.
Section 3. The 3 zones of protection.
So now that our relay knows how to spot a fault geometrically, we need to talk strategy, because you never ever want to rely on just a single line of defense. Engineers developed a brilliant system of overlapping coverage called stepped distance protection. Notice how the coverage doesn't just stop at the end of one line. Zone 1 acts as your primary, immediate defender. Zone 2 reaches out a bit further, providing backup. And Zone 3 reaches all the way across the adjacent lines. They cover each other's blind spots just like a perfectly coordinated sports team.
Let's break down the hard rules for this stepped system. Zone 1 covers exactly 85% of the transmission line, and it trips instantly. Now you might be asking, why only 85%? Well, because our measurements aren't actual magic. We leave a deliberate 15% blind spot at the far end so we don't accidentally trip the next line's breaker for a fault that isn't even ours. Zone 2 then steps in to cover that 15% blind spot by extending out to 120% of the line, but, and this is absolutely key, it intentionally waits before taking action.
That waiting period is typically around 0.5 seconds. Now, I know half a second sounds like a literal blink of an eye to you and me, but in the world of electrical engineering, half a second is an absolute eternity. Zone 2 waits for this specific amount of time to give the primary relay at the far end a chance to see the fault and clear it first. It's basically a polite, highly disciplined system of, hey, you go first, but if you don't handle it, I absolutely will.
Section 4. Speeding up the defense.
The thing is, polite and disciplined isn't always good enough. As grids got larger and a lot more heavily loaded, engineers realized this strict zone system had some terrifying flaws. For instance, what happens if a catastrophic short circuit hits at exactly 99% of the transmission line? That's right in that 15% blind spot we purposely left for Zone 1. That means the local relay has to just sit there and wait for its Zone 2 timer to run out. Sitting around for half a second while a massive fault rips through the grid is just too slow. Equipment melts, lines dropped, instability ripples out everywhere. We need speed.
So the fix here is actually getting these relays to talk to each other. Enter the PUT system, which stands for Permissive Underreach Transfer Trip. It's essentially a high-speed communication channel, usually over fiber optics or microwave, linking the two ends of the line. If the relay at the far end sees a severe fault in its instant Zone 1, it immediately fires off a carrier signal to our local relay. The second our relay gets that signal, it completely bypasses that half-second delay of Zone 2 and triggers an instant high-speed trip. Teamwork literally saves the grid.
But you know, even blazing fast communication can't always solve human error. Consider this really scary edge case. Let's say a maintenance crew powers down a line and attaches heavy grounding cables so they can do some safe repair work. They finish up, pack up the trucks, but oops, they accidentally forget to remove those grounding cables. Then, the operator back at the control center throws the switch to turn the power back on, literally closing the breaker directly into a massive three-phase short circuit. That brings us to switch on to fault.
Closing into a grounded line creates a uniquely dangerous zero-voltage nightmare. Because the fault is perfectly solid right at the very start, there is virtually zero voltage present the exact instant the breaker closes. Remember our math from earlier? The relay strictly needs voltage to calculate impedance. Without a voltage reference, the normal distance zones go completely blind. They might not trip at all. To solve this, modern relays use switch-on default, or SOTF logic. It utilizes a clever memory feature of what the voltage was just before the line was de-energized. This allows it to instantly recognize the dead short and trip the circuit before disaster strikes.
Section 5. Backups and breaker failures. Okay, we've covered the math, the zones, and the communications. But we have to face the absolute darkest scenario for any grid engineer. What happens when the relay does its job perfectly, sends the trip command, but the actual physical mechanical circuit breaker jams and just fails to open? Well, here is the chronological cascade. First, the distance relay detects the fault and commands a trip. Second, a timer starts and the system watches the current. If dangerous fault current is still flowing after a pre-selected delay, the system confirms the physical breaker is broken. This is terrifying, so step 3 invokes the nuclear option, the 86BF lockout relay. It doesn't bother trying the broken breaker again, it immediately sends trip commands to every single other breaker connected to that local substation bus. It intentionally sacrifices the entire local substation just to isolate the massive failure and save the wider grid.
It is honestly incredible when you realize that every second of every single day, these invisible layers of logic, math, and high-speed communication are silently watching over our world.
As we add way more renewable energy and face wilder, more unpredictable weather, the grid is only going to get more complicated. The next generation of digital relays will need to be even smarter and even faster. The engineering we explored today is absolutely brilliant, but it really begs the question, as the systems managing our power become as incredibly complex as the power itself, who is protecting the protectors? What new, unimagined protections will we have to invent just to keep the lights on tomorrow? Let that spark your curiosity until next time.